All right, so at this point, so we've seen a bit of the human visual system, and we talked about degrading the picture and trying to see what we can conceal or not. And obviously, when we do that, it's a bit hand-wavy. Okay, we need something a bit more tangible, so we need some metrics. We need to be able to publish a paper or sell a product and say this is 10% better than the rest. So we need some numbers, okay? And this is the bad news here, okay? So the only way really to do that properly is to go through subjective assessment. So you basically organize some kind of psychological test. So you have, 50 people, and you have calibrated TVs. You sit the people in front of the TV at the correct angle, correct distance, and then you ask them to go through a very long process that might take an hour or two, and they watch some very boring videos, and they have to mark them from 1 to 5, and they got some tests, and it's the whole procedure there, and just by the name of so it's been standardized, and it's called ITUR BT 511, and just by the name there, you realize how cumbersome it is and how annoying it is to set up, okay? And even so to a point, like very few people actually conduct this kind of test, and even if you look at companies such as YouTube or Netflix, they actually don't do that at a large scale. They only do that at a very small scale, as universities will do, for instance, okay? So it's quite complex, but very useful, okay? That's the only way to really properly do it, to ask people to judge what the difference between two pictures. Now, obviously, you cannot do that on everything, and you cannot do that for your labs, for instance, so we need to come up with different ways of doing that. And here comes the objective metrics. So I put objective in quotes because let's put it this way, it's like you have a referee, you have a judge, and here we're not asking for a very fair judge, we're just asking for a very consistent judge, okay? So we're looking for, by objective we mean something very consistent, okay? Doesn't mean it's a good metric. So the first one, so all these metrics are the usual suspects that you have in signal processing. So the first one would be the mean square, okay? So you have, say your picture is I, and so the x here is so x is the pixel coordinates in 2D, and I say, well, I'm going to look at my picture and all the color channels, and I will compare that against the degraded picture, and I'm going to do the average of the square differences, okay? And that's fine. So that's very classic matrix called the MSC, right? But we know it's not a very good one. A better one probably is the mean absolute error, MAE, which is the same, but this time to detect the absolute difference between the pixels. Right, so that's all fine. Another classic one, and possibly even more classic, is the SNR and PSNR. So, sorry. So what you measure here is the sum of you take the ratio of the squared of your signal divided by the mean squared error. And that kind of comes back a bit to Weber's law and so on. You're trying to take a ratio between the difference and so that would be your MSC and the magnitude of your signal here. So that's the signal to noise ratio, and so that's in log space, right? And then you have the PSNR, and the PSNR is really what we use all the time. So we just normalize, instead of taking the magnitude of the signal, the pixels, we actually normalize that by the maximum value, which we know is 255, okay? And so PSNR is expressed in dBs, and typically if you have, say, 40 dB, okay, that means you almost have no difference. And if you have 20 dBs, it means it's a really horrible picture, okay? So small dB, okay, so if you have 20 or 25, it's not very good, okay? If you have 40, this is pretty good. Okay? So PSNR is quite a popular one. However, okay, so these metrics, the reason why people use them is because they are consistent, very easy to express, very they have a broad spectrum of, they're quite simple, so they can be applied for many different situations. But we know they're not really how we perceive images, okay? And this is an example of, and so the original picture is on the top left here. And there's like 5 different types of degradations you see here, okay? So they kind of rank from the least noticeable to the most noticeable. And the mean square error you have, so basically we took this picture and subtracted this other picture and did the average of the intensity square differences. It's roughly the same from on all of them, okay? So mean square error for 144, if you take the square root of that, that's, I don't know, 12, something like that. So it means you have an average of difference intensity of 12 between the two values, okay? So remember the values range between 0 and 255, and here you have a difference of 12 roughly between pixels here and pixels here. And it's not very noticeable, it's not like a major difference here, because actually what is happening between the two is like you only have an offset. So all the pixels, all the intensities have been offset by the same value of 12, I guess. And because it's a global thing, the brain is not very good at spotting that. It's not a major difference to your eyes. In this picture here, I think they changed the contrast. And then on this one, on the bottom left, you have some, it's called salt and pepper noise. So you have a number of pixels that have been flipped to white or black. Okay, so all the other pixels are the same, but just a number of pixels have been flipped to white or black. So this is starting to be quite distracting. Here we totally blurred the picture, and here's like a massive JPEG compression artifact. Okay. So psychologically, this is not the same type of error. Okay. So this error here, the degradation you have here, is much less pronounced for us than this one, for instance. Okay. And but the error, the objective metric tells you the same. And so that's a problem. So people have known that for quite a while, and so that's why when you see people reporting codec performances and so on, usually they don't just use one technique, they use like multiple different metrics, and you can't really put your faith into one metric because it's very easy to trick that metric, okay? It's very easy to get good results for that metric, but then very bad for very bad impression overall. So these images actually come from a paper on one particular metric called SSIM. That was in 2004, I think. And basically, what they've done in that paper, they say, we need to have a proper metric that takes into account most of the psychovisual knowledge we have. And so they've done the proper exercise of doing this calibration I talked about, so this very annoying process here. And so it's called the MOS score usually. And so you have rank from 1 to 5. And so they had people marking a bunch of pictures, and they had data, kind of a ground truth reference of what types of artifacts people find annoying and so on, and they had the human results on that. And then they devised a technique using image processing techniques. I won't go into detail here, but they're not very complicated. And they're trying to match, to regress their technique to the curve that they obtain to what the humans will find. Okay, so they're trying to come up with a formula that will kind of match what the human perception is. And this is SSIM. Okay, so SSIM, we said that the first one has a score of 0.988, and this is, by the way, a score of similarity. So MSC is a score of dissimilarity. So the higher it goes, the more dissimilar you are. So MSC of 0 means it's the same. MSC of plenty means it's very much different. So SSIM goes the other way around. So 1 means you're perfectly identical, and 0 means you're very much different. And you can see the numbers go down as you go down. And so the JPEG compressed on the bottom right is 0.6, which is pretty poor. But the one on the top left which is just an offset on the brightness, it's very close to 1, which makes sense, you know. So that's SSIM, which is now a well-established metric, but people still go back to the objective metrics. It's not like if everybody uses SSIM and not using the other metrics. It's more that people now publish both the SSIM and the other metrics. Right. So this is something, if you do 5C1 next year, if you stay here, that would be a bit more in depth into this kind of metric. For video, something similar happened, and it's only very recently that there's been a paper on that. The similar idea, so that was on images. Now on videos, you have all sorts of different types of artifacts. And here's the problem, you know, you have 2 compression, and they both have the same bit rate. And so on the top, you have a version which is quite heavily compressed, and the second one is a bit better. And the PSNR is roughly the same, okay? And so if you look at the one on the top, it says it's 31 dB. It's actually worse than the one on the bottom, which is 34. But for instance, for the crowd picture on the left, it's not obvious that one is worse than the other, whereas on the cartoon picture, it's much more obvious. All right? So same problem applies, but you would have a number of different issues with temporal aspects and so on. So the same team and people at Netflix, because Netflix was very much interested in delivering the best quality of the video possible. So they developed this metric called VMAF, and it's kind of a similar idea than SSIM. What they've done is they've done perceptual studies, and they had people recording how they felt about the shots and difference. And then what they've done is they looked at a number of existing algorithms for assessing metrics, and they used machine learning, in this case SVM regressor, for trying to find a formula that will try to emulate or replicate what the humans are doing. All right, so we've introduced just summary. So we've looked at RGB, we looked at YUV. So YUV is what we'll be using principally in compression, okay, just to let you know. And we looked at a number of aspects of the human visual systems and see how the contrast sensitivity changes with frequency, okay, spatial frequency. And we know that there is this, definitely, especially for chrominance, that we're not very sensitive to high changes, fast changes in chrominance. So it gives us good hope that we can do something with chrominance much aggressively than with luminance. And we looked at a thing called activity masking, which is something we talked about yesterday, which was where you put the noise matters, okay? So if you put noise on something flat, then you see it. If you put noise, would degrade your picture in a busy part of the picture, then you probably will get away with that.